My name is Melissa Lane, and I'm honored to introduce our next speaker, who is currently the head of Combat Services Integration Division with the Mission Integration Directorate at the National Reconnaissance Office. In prior assignments, he led advanced R&D teams for small satellites and optical systems at the NRO and managed a broad portfolio of basic research grants at the Air Force Office of Scientific Research. Also a contributing author in the inaugural issue of Space Education and Strategic Studies Journal. It is my distinct pleasure to introduce Major Kevin Pohl.
Thank you very much, Melissa. So yeah, the bio is out of the way. So what I'll be talking about today is a project that I've been researching for the past couple of years, and that is the use of long-wave infrared polarization for space object detection and characterization. So let me go ahead and share my screen here. Yes, this one. There we go. And I'll pop it into slideshow mode. No, that's not quite what I had in mind. See, are you seeing the entire screen or just the presentation?
I can see the entire screen, but we can also see the presentation. I mean, it's fine. We can clearly see it.
Okay. Yeah, I just want to make sure. I was expecting it to just go into standard slideshow mode, but this will do. This will do. So, fundamentally, there is, I don't want to call it a problem, but there's an issue today with space situational awareness of there is a distinct small number of sensors available. They do very good things, but they do have some limitations. In particular, they're A, expensive, and B, in many cases difficult to set up, even if you had the money available. So by and large, there are two types of sensors for space situational awareness. On the one hand, you have large, powerful radars. On the other hand, you have optical telescopes of various kinds. And for the most part, they're government owned. There are some private as well. As far as getting data to people that need to know where things are in orbit, the government obviously has their own way of doing this. There's also a great deal of voluntary sharing of data between various organizations that maintain space object catalogs. Now, the coverage and responsiveness are limited by the geographical location of the sensors. So, for example, we had our old space fence that stretched across part of the southern U.S. We have our new space fence, which is located in a couple of choice locations. There are, telescopes in Hawaii and a couple of other locations that can offer specific services, but it's not easy to get a big picture of what's going on at any given point in time and over any given location on the planet. So where my research is directed is, well, is there a way of having a simpler system that can be proliferated to lots of places without needing large investments in either time, money, or regulatory activities? This is where the use of long-wave infrared polarimetry comes into play. Because on the one hand, you can have short exposure time, so you can do quick snapshots, but it's day-night capable because your target is itself the light source rather than relying on solar illumination. And it's a completely passive sensor, so you don't have issues of you can only turn your rate, going through the regulatory hassles of having a strong emitter of RF energy in a place, or wanting to put up a laser somewhere and having to keep it out of the path of airplanes and such. So the idea is to have something a little bit simpler. So the next slide, I talk a little bit about the basics of polarimetry. The point is not to make this seem like it's really simple conceptually, in that you're basically making six flux measurements using ideal polarizers in front of a radiometer. And there are many ways of implementing that in practical use. But essentially, you're collecting the measuring the horizontally polarized flux, the vertically polarized flux, diagonals at 45 and 135 degrees. And if you wanted to, you can also measure the left and right circular polarized flux for optical applications in the thermal infrared wave bands. That's not really relevant because they constitute about 2 orders of magnitude less flux than the horizontal, vertical, and diagonal polarizations. Once you have those measured, then you can essentially convert them to color spaces. So that would be taking your S1, the difference between the horizontal and vertical polarization flux, divide that by the total thermal flux, so that's your S0. You can do the same with the diagonal polarizations, and you can also create a separate color space looking at just the ratio of diagonal polarization to horizontal vertical polarization. Now, these data are then normalized, and now you can compare color spaces to each other. So that gives us 3 separate comparisons, if you will. The S2 over S0 versus S1 over S0, and then S2 over S1 versus S1 over S0 and versus S2 over S0. The next step is to quantify the difference between the distribution of measurements. And for that, if you look at the pictures here, you can see the means are separated from each other. And an initial stab might be, well, just look at the actual distance, the Euclidean distance between the 2 points. But that doesn't give you the whole picture. To properly differentiate between the distributions, the use of a statistical distance measure is a better choice. And for this purpose, I chose the Bhattacharya distance, which is in the bottom left-hand corner. The first term of that is a slight modification of the very frequently used Mahalanobis distance. But that part is really useful in determining whether a specific point is the same as or far away from a distribution of points. What the Bhattacharya distance does is it is able to take 2 collections of points and determine whether they're similar to each other or not. And so that's what we've done here. If we go to the next slide. So we'll come back to that in a little bit. But what I did for my modeling and simulation is I created a primary vehicle and a secondary vehicle. And for the primary vehicle, there are 2 versions. Or actually, technically 4 versions total. But I have a cube-shaped version. I have a more elongated cuboid-shaped version, and each one of those comes with an bare aluminum bus or a Kapton-coated bus segment. All the other components are essentially the same. And then there's a secondary vehicle that is substantially smaller than the primary vehicle. And that one has some aluminum surfaces, some Kapton coated surfaces, and some solar panel covered surfaces. And that secondary vehicle is roughly half the size of the primary. So I ran took hundreds of measurements in simulation. In each case, looking at the vehicle from a variety of angles. In real life, if you were aiming this at a low Earth orbit satellite, every time you measured it, essentially, you would be looking at a slightly different angle of the vehicle. In the past, the same methodology has been studied looking at geostationary objects using visible light polarimetry. And in that case, you're looking at an object that really isn't moving. You're always looking at the same, for the most part, the same surfaces. The only difference is over time, the angle of the solar panels will change. So on one of those, as you're looking at it over time, you're really just looking at the change in the direction of the solar panel gives you the variation in polarimetric response. Whereas here, I'm looking at the vehicle from a variety of sides. So I start and at one side, plus 30 degrees off the center line, and then I have my camera rotating all the way around to minus 30 degrees. So 30 degrees to the other side of the center line. And then I take those sets of measurements, that distribution of measurements, and I compare first one of the primary vehicles with itself. Sorry, one of the primary vehicles, and then with the secondary vehicle in the scene, and compare that to the primary vehicle just by itself. And what you can see here in the graphs is that in each case, there is a distinct difference between the distribution with the secondary vehicle and the distribution without the secondary vehicle. Now, if you look at the three graphs that we have here, the first graph, the S2 over S0 versus S1 over S0, looks, just as an intuitive, I look at the graph, I can see, yeah, the points are in different places. If you look at the other two, the points, especially in the S2, S1 versus S1, S0, the points are much more similarly distributed, with one or two outliers making up the bulk of the difference. And so that's where we get into, yeah, if you just look at the graph, the means of the distributions look about the same distance away, but in this case, the distributions are actually far more similar to each other than the spacing of the means would indicate. So there is still a little bit of ambiguity in all of this, because you might have two of the comparisons looking very distant, and you might have a third one that kind of looks the same. So I'm still working through, is it just believe the best out of two? If just one of them is sufficiently different, is that the main criterion? Now, one thing I can say is that from all the measurements that I have taken and the comparisons that I've made, the S2 over S0 versus S1 over S0 seems to be the most consistent with what I know to be ground truth. And then we can do the same measurements. So the first one was with the secondary vehicle off to the side and fully visible as I'm looking at it from the front. I can do the same sets of measurements with the vehicle partially obscured. So if you think of it in In simple terms, the vehicle is kind of hidden a little bit behind the primary. So as I start my measurements, I really can't see the secondary vehicle, and as I work my way over to the other side, it comes into full view. And there again, for one thing, the overall statistical distances that are measured are much smaller, as would be expected, because at least part of the distribution should completely overlap. But for the other thing, you can see if you look at the first graph up here, this structure here looks an awful lot like this structure here. And so that's part of what drives the similarity and the lower statistical distance. So that was all looking at the vehicle with a Kapton covered bus. We can do the same thing with an aluminum covered bus. And there I found that the statistical distances tended to be a lot smaller. And part of the reason for that is that the light emitted by the aluminum bus tends to be more strongly polarized than that emitted by the Kapton bus. And so adding a new signal to a larger signal is going to result in less of a difference between the two measurements. So that obviously, it doesn't necessarily have an impact on a potential use of this in an operational sense, because nothing that actually flies in space is, made completely of aluminum. They do tend to have other coating materials on the outside, but it is a data point, a thing to keep in mind, that while you can theoretically detect the presence of something else in the scene near your space object, it's also entirely possible that if it gets close enough and your primary object is a relatively stronger emitter of polarized light, your primary object may very well drown out the signal of the secondary object. So, as far as conclusions, with the caveat of what I just said, this method does allow the discrimination between a known object and that same object with something else nearby. However, it's important that you have enough, that you can see enough of the secondary object for long enough to clearly, clearly say that there's a difference in what you're measuring. This method is definitely better suited to LEO applications than GEO applications, just because the scene diversity is severely limited by the way those orbits work. If you wanted to, you could very easily put something behind a GEO object and no one would ever see it, because there would be no line of sight to it, and therefore even this method would not succeed in detecting anything. Whereas in LEO, because you'll see objects from various angles over the course of multiple passes over a ground site, and the way orbitology works in low Earth orbit, you'll definitely get a chance to see whatever is nearby, things that you care about. So some future work is to further refine the simulation to incorporate more materials and shapes. I worked off a relatively small set of materials just for simplicity's sake. And I was, using basic textbook references of the polarization properties of those materials. Obviously, if you wanted to use this for a vehicle that you had up in space, you could go through and do those characterizations specifically for the object that you care about. And the second piece maybe and a bit of a larger effort is, a separate modeling of what would be the optimum number and distribution of ground sensors to provide solid coverage of low Earth orbit. Now we're talking small things, telescopes on the order of maybe 50 to 70 centimeters in diameter, as opposed to the really big telescopes like you see in national observatories and such. But it would still be a bit of an investment to proliferate those on a global scale. So finally, I also want to put in a plug for the Aerospace and Ocean Systems Laboratory at Virginia Tech. They do a whole host of very interesting applications, not just in space. They also have a strong cyber component and a very good educational CubeSat small satellite team with their own ground stations, frequent CubeSat launches, certainly a couple of them going up every couple of years, in addition to sounding rocket and other activities. And they also work closely with a variety of government organizations as well. So with that, I'll go ahead and end my briefing, but I'm going to open the floor to any questions you might have.
Okay, Kevin, we have a couple questions here. One from Mike. Do you have an opinion on the status of the U.S. satellite system currently? Is the U.S. still competitive from an engineering perspective when it comes to satellites? Are there any concerns for the long road?
Well, I'd say they're definitely competitive. There's certainly, I don't see any reason to think that we're lagging behind anybody else. There's always concerns, obviously. There's the questions of, can I get my thing funded? If I get my thing funded, can I actually finish the program? Or does it get chopped at some point because funding goes away? I mean, that's kind of the fundamental problem that anybody faces with something that requires such large investments. But overall, I'd say we're in as good a position as anybody else.
Okay, we've got another question by Sumedra. Could you provide details on the FOV used in the model and model distance of the observation platform from the vehicles suitable for LEO?
Well, so the target distance, the models that I ran were essentially reproducing a lab bench setup. So I have a camera that's modeled as being a few meters away from the target. But fundamentally, I'm modeling that as a single pixel measurement, rather than having a high definition picture of the model. I'm really just measuring the overall flux from the 1 pixel. So the goal is to have it representative of modeling a telescope on the ground and the targets around 400 kilometers away, give or take. That being, 400, 500 kilometers being the standard LEO, low Earth orbit distance. So the field of view for what I'm modeling is not entirely representative, I guess, right? Because I haven't simulated the ground through the atmosphere to a space object, but the idea is, if I remember correctly, we were looking at something like 5 or 10 meters resolution at LEO altitude from the perspective of a ground-based telescope. So you would have a large telescope, something like Hubble or worldview or something would sort of maybe fill a pixel, right? And most other things would be much smaller. One advantage and why this still works, despite the fact that you're not getting that much flux, is that there's very little competing flux to deal with. So you're not concerned with reflections from the sun, because the emission from the target object is going to be substantially higher than the reflections, and the background is essentially non-existent. There's very little thermal IR just floating around in the sky.
Any other questions? Okay. Well, thank you, Kevin. I'm hoping you will continue publishing your work with the CISA Journal.
Mm-hmm.
This is great stuff, and your research is very, very important. Stay with us. The Plenary Endurance by Lockheed Martin's Stacy Kubitschek starts at 2:40. Thank you.
Well, thank you very much.